Swayam Prabha. Digital India. Educated India.
Friends, welcome to the 32nd lecture on advanced steel design. We are discussing about derivation of stability functions. In this lecture, we will continue to discuss that with some more interesting details about difference between buckling and stability. Okay. So, friends, while discussing the stability functions, we already said we will compare a standard fixed beam which is used in stiffness method of matrix analysis. Okay. So, the basic module which is used to analyze a statically indeterminate beam or a frame or a structure is a fixed beam with some prismatic cross section and A. So, we have used this as a standard nomenclature and we said that I can give unit rotation at different ends and displacements and try to derive the stiffness matrix. So, the standard fixed beam has got 4 degrees of freedom kinematically, that is theta p, theta q and del r and del s. Okay. The member is prismatic with its EI, L and A. So, now this is a jth end of the member and kth end of the member. So, from J running towards K is xm and ym is anti-clockwise 90 to xm. This is a standard convention which we have said. Okay. Now, I want to derive the stiffness coefficient for this beam, which is statically indeterminate, which is a fixed beam, we know that. So, we know Kij, the stiffness coefficient, is the force in ith degree of freedom for unit displacement in jth degree of freedom, keeping all other degrees of freedom restrained. We know this. Okay. So, what we did is, we gave unit displacement rotation in pth degree and we marked these forces as Kpp, Kqp, Krp and Ksp. Is it not? So, the in Kpp, for example, here the first subscript stands for the place or the degree of freedom where measuring the force, which is P, and the second subscript refers to the degree of freedom where you are giving unit rotation. So, theta p is unity, therefore, it is P. You will find in figure 1 the second subscript of all is P. Okay. So, unit rotation at jth end, unit rotation at kth end, unit displacement at jth end and unit displacement at kth end. So, standard convention, we derive the stiffness matrix for this and we said the stiffness matrix for a fixed beam neglecting axial deformation is given by this. So, 4 by 4 matrix. So, standard derivation, you can refer to my book on analysis of structures using MATLAB written by for CRC. This book is a very popular book and this gives you the MATLAB program for doing analysis of indeterminate structures using stiffness method. Please refer to this book, and MATLAB programs can be downloaded free. I can use this book as an important reference for teaching and research as well. So, this book refers the derivation of this in detail, but let us say this is my P, Q, R and S labels, and we know this is KPP, this is KQP, and this is sum of these two. So, I should say is KPP plus KQP by L. And the fourth one is negative of this. The second column is just the cross of this. So, this becomes KPQ and this is KQQ, okay, and sum of these two by L will be here. So, KPQ plus KQQ by L. The fourth one is negative of this. Coming to the third column of this matrix, sum of these two by L will be here. Incidentally friends, this value and this value are same because stiffness matrix is symmetric, okay, but do not go by that. There are possibilities where the stiffness matrix can become asymmetric as well. So, let us not bother about that. So, sum of these two by L is here, which is KQP plus KQQ by L, okay. Then sum of these two by L further is here, which is KPP plus KPQ plus KQP plus KQQ by L square, because there is already an L here, I am dividing it further by L, and the fourth one is negative of this. The fourth column is very straightforward, negative of the third column. Okay, this is standard derivation. We have not done this derivation in this course, but it is a standard derivation available in all standard reference books which are meant for analysis of indeterminate structures using stiffness method. Okay. So, I am going to borrow the same algorithm and we explained that in the previous lectures. I am just summarizing it now so that stability functions can be easily remembered friends. That is very important, because generally stability is an area or is a topic of discussion which is having a lot of confusion. People do not feel it very comfortable to teach in the PG course or definitely not in UG course, UG level, and in research it is handled with most complicated manner. So, the fundamental reason for this is the stability functions and the approach of stability problem is not understood properly. Okay. So, let us deprive of this particular feeling, get out of this and try to remember this from the basic understanding of a simple statically indeterminate structure, which we already know. Okay. So, I am following the same algorithm, how we did the derivation for this. Okay. So, what we did is, instead of giving the rotations of this, Okay. We started finding out this using flexibility method, and we also wrote this equation for us in the previous lecture, and we said that my K matrix for a simple fixed beam neglecting axial deformation is given by this. Let us have the labels as P, Q, R and S. This is Q, okay. Let us say we know this is 4, 2, 6 by L, 4 by L, 4 by L, 6 by L minus 6 by L square. So, 2 by L, 4 by L, 6 by L minus 6 by L square, 6 by L square, 6 by L square, 12 by L cube minus 12 by L cube, minus 6 by L square, minus 6 by L square, minus 12 by L cube plus 12 by L cube. I am following the same logic as we have explained here to this. Okay. We have used the same form. I want you to remember this form, and I will correlate this form to the stability functions now. That is what we are going to do. So, that if you remember this form, you can always remember the stability functions form, that is what it is. So, what we did is, we took the same fixed beam, of theta p, theta q, del r and del s of A, E, L I etc., but we added one new concept here. We said I am applying an axial force because I am studying stability. Okay, we applied an axial force, right. So, we gave unit rotation at jth end, then we wrote the free body, the equation for the free body diagram at the displaced position under the presence of axial load. We started with axial compressive load, okay, and we derived the rotational functions, okay. That is what we did. We derived the rotation function using second order ordinary differential equation from the 3A flexure, okay, and we found out the rotation coefficients from the solution, and we said Ri is alpha I times of sin alpha I minus alpha I cos alpha I by 2 times of 1 minus cos alpha I minus alpha I sin alpha I. This was the Ri, and Ci we derived as alpha I minus sin alpha I by sin alpha I minus alpha I cos alpha. We derived this, okay. They are called as rotation functions. Why rotation functions? We derived this by giving unit rotation, okay, we derived this. We also proved at axial force 0, at axial load 0, we showed that, I will write it here, Ri at phi I 0, axial load 0 is 4, and Ci at phi I 0 is 0.5, is it not? We used L'Hospital's rule, then we derived this. Then subsequently friends, if you recollect, we gave rotation at the kth end and derived the coefficients simultaneously, and we found out that for this particular case Kpp was found to be Ri times of Ei by Li, Kqp was found to be Ci times of Kpp, which is Ci times of Ri of Ei by Li, okay. And we said Krp is Ri 1 plus Ci Ei by Li square, and Ksp, which is here, was minus Krp. We derived this, is it not? Then we gave unit rotation to the kth end, derived the stiffness matrix in the same. Then we said Kpq, which is here, is now Ci Ri Ei by Li, whereas Kqq is Ri Ei by Li, and Krq is 1 plus Ci of Ri Ei by Li square, okay, and Ksq is minus of Krq. We got this, okay. Then we also did for tensile load. We also did for tensile load, and we expressed beta as a function of alpha, and we worked out we should say axial tensile load. We got Ri as alpha I of alpha I cos hyperbolic alpha I minus sin hyperbolic alpha I by twice of 1 minus cos hyperbolic alpha I plus alpha I sin hyperbolic alpha I, and Ci was found to be alpha I minus sin hyperbolic alpha I by sin hyperbolic alpha I minus alpha I cos hyperbolic alpha. We got this, isn't it? Okay. So, we use this, then we started working on translational coefficients. So, we worked on translational coefficients, functions, let us say, under axial compressive load, so we gave unit displacement at R. We also did same way in S as well, and these forces generated Kpr, Kqr, Krr and Ksr were determined for this free body diagram, is it not? We found that Kpr is same as Kqr, which is same as Ri into 1 plus Ci of Ei by Li square, okay, and Krr is 2 Ri 1 plus Ci of Ei by LIQ, and KSR is minus of KR. This is what we derived. Am I right? We wanted to express this as a function of translational constant. So, we said also let KRR be expressed as Ti times of 2Ri 1 plus Ci Ei by LIQ, okay, where Ti is called as translation function. We also say this is minus of KSR. Sorry, we should write this way. KSR is minus of KR. We follow the same logic here, okay, where Ti is a translation function which was given by Ti is equal to 1 minus pi square phi I 2 Ri 1 plus Ca. Remember, phi is a multiplier or the ratio between the axial load and the Euler's buckling load, okay. That is the ratio. I think we already know this equation, how phi is connecting Pa and Pe. So, we derived this. After deriving this, we summarize these constants, okay. We summarize them and we wrote it in a matrix form which is quite convenient and which resembles the same. I am writing the matrix form here, the stiffness matrix for stability function, okay. Ei times of okay, Ri by Li, Ci Ri by Li. Let us okay. Then I am using the same logic. See here how we wrote this. Sum of these two by L was this, and this is negative of this, is it not? That is what we did. I am using the same algorithm here. Sum of these two by L, that is 1 plus Ci of Ri by Li square, and this is minus of Ri by Li square 1 plus Ci. I am using the same logic. If you look at this is crossed, is it not? See here, this is crossed. So, I will cross it here, I will cross this here. So, I am writing this as Ci Ri by Li, this is simply Ri by Li. In fact, that is what you will get here, see here. KPP, KQP, this is the first column, okay. The second column will be KQQ is Ri Ei by Li. I am doing the same thing. This is P, this is Q, R and S. Okay. So, I am looking for, let us say KPQ, I am looking for KPQ, okay, KPQ. Let us see here. KPQ is Cari Ei by Li, Cari Ei by Li, okay. So, I am doing the same thing. I am just, so I am making you to easily remember this equation, that is what I am trying to do, okay, similar to what we wrote in the beam analysis. So, once we do this, sum of these two will be here by L. So, that is 1 plus Ci of Ri by Li square, then minus of this Ri by Li square 1 plus Ci. Now, If you look at the third value here, sum of these two by Li. So, Ri times of 1 plus Ci by Li square, sum of these two by Li. So, that is Ri 1 plus Ci times of by Li square. This is what we did in the beam also, is it not? See here. Sum of these two by L is this. Sum of these two by L is this. Okay. Sum of these two by L is this. Same way here. Sum of these two by L will be this, which will be 2 times of Ri 1 plus Ci by Li cube. Since it is a translation function, I put Ti here. Okay, let me do it in different color. I am putting Ti here. Okay, so therefore, this will be minus 2 Ti of Ri of 1 plus Ci Li cube. The fourth column, as you see here, is negative of the third column. See here, I am doing the same thing here, negative of the third column. So, minus of Ri 1 plus Ci by Li square, minus of Ri 1 plus Ci by Li square, minus of 2 Ti Ri 1 plus Ci by Li cube plus of 2 Ti Ri 1 plus Ci by Li cube. Friends, it is very easy to remember this matrix if you remember this matrix. So, I have conveniently mapped for your convenience of at least remembering a standard beam derivation, which is a fixed beam, to a stability function which is much more complicated derivation. See, the derivation is complicated, but you can remember this equation very well without any mistake. And whereas these Ri and Ci values are already given, okay, we already derived them, you can remember them, right. Now, having said this, now we have established a perfect correlation between a standard fixed beam used for static indeterminate analysis with that of a problem with axial load to derive stability functions. That is a perfect correlation, isn't it? So, this has got to be clearly understood, and one can also plot this Ri, Ci and Ti values for different phi. This is called stability chart, which I showed you in the last lecture. So, we have a program available in the textbook written by me, which is referred in this course. It has got a MATLAB program. The MATLAB program will help you to generate this chart, okay, in Excel sheet. It can also plot, which I am going to use it for solving the problems in this coming lectures. Okay. Now, the question comes, friends, people like to know what is the difference between buckling and stability. Okay. Friends, instability can be assessed based on the following: 1, material property; geometric conditions. 3. Nature and magnitude of the loads acting on the structure. Okay, it's a standard thing. Therefore, friends, having said this, assessment based on material strength highlights whether the applied load exceeds the acceptable strength level of the material. Okay, this classifies, or this assessment classifies whether the structure is stable or not. Okay. Now, assessment based on geometric configuration. Explores the functional success of the member. It explores the success even under, that is a very important condition here, friends, even under the displaced configuration. Okay. This is what we say as dynamic stability. Therefore, friends, in general, loss of stability is assumed or is assessed in terms of load deformation relationship. Okay. So, loss of stability arising either from change in geometry or change in structural configuration lead to further classifications of instability. What are they? They are flexural buckling, torsional buckling, flexural, torsional buckling, lateral, torsional buckling. So, friends, we are slowly connecting stability to buckling. Okay? So, very clearly loss of stability will lead to classifications of buckling actually. Okay? Instability leads to classification of buckling. Okay? That is what, how they are connected to. Okay? Furthermore, it is important to note that structural system remains in rest before instability occurs. Okay. Also remains in rest immediately after the failure is initiated by buckling. So, instability will initiate a failure and buckling is a failure. Instability is a geometric displacement, it is a geometric imbalance. The consequence of instability is buckling. Okay? There are 4 methods to solve buckling problems. One, equilibrium state approach. 2, work approach. 3, energy approach. 4, dynamic approach. So, we have connected, bridged the understanding between stability and buckling, is it not? So, let us see what we learned from this lecture. We have learned how a standard fixed beam derivation is connected to stability function derivation. We have remembered the matrix with respect to the stability function, and we realize that it is very easy and it is having a one-to-one mapping. We have also learnt the difference between stability and buckling, and we realize that buckling is a failure mode, is actually consequence of instability. Okay? So, in the next lecture we will take up some problems, use MATLAB to find out how to check stability of a given structural system. Okay? We will do some examples. Thank you very much and have a good day.